This research paper introduces a novel approximation method for solving stochastic differential equations, SDEs, which are mathematical models used to describe phenomena involving random noisy perturbations. The proposed method utilizes quadratic polynomials to approximate the solution between two successive intervals, and it is shown that this approach can provide promising results in solving SDE problems. The paper begins by discussing the challenges of modeling real-world phenomena using ordinary differential equations, ODEs, and highlights the importance of SDEs in various fields such as theoretical physics, molecular biology, population dynamics, and mathematical finance. It also reviews existing stochastic schemes like the Euler-Maruyama, M, and Milstein methods, which are commonly used to simulate sample paths of SDEs numerically. The methodology section explains how to use quadratic approximating functions to develop the algorithm. It focuses on the equation for geometric Brownian motion, which is a basic model in financial mathematics that describes the time evolution of financial variables. The analysis of stability, consistency, and convergence of the proposed method is presented in detail, demonstrating its efficiency and accuracy compared to traditional methods. The validity and effectiveness of the proposed strategy are tested in the following section, where numerical experiments are conducted to compare the performance of the new method with existing ones. The results show that the quadratic polynomial approximation method outperforms other schemes in terms of computational cost and accuracy, making it a promising tool for solving SDEs. Finally, the paper concludes with a discussion about the obtained results and suggests potential future work directions. It emphasizes the need for further research on improving the proposed method and its applications in different domains. The overall summary highlights the significance of this novel approach in advancing the field of stochastic differential equations and its potential impact on various disciplines. Here is the combined summary of pages 3 and 4. The proposed method for integrating the system involves subdividing the interval 0, t, into subintervals obtained from a regular partition, where n is an even number. The goal is to obtain the values of the function x, t, at the next two time steps t2n plus 1 and t2n plus 2, given the approximate numerical values of x, t, at the grid points t, I equals 0, 1, 2n. The method involves integrating equation 7 on t2n, t2n plus 2, and t2n, t2n plus 1, respectively, and approximating x, t, in these intervals using quadratic interpolation functions. The interpolation functions psi(n), j, t, and psi(n), j, t, are defined by equations 10 and 15, respectively. Substituting the interpolation functions into the integrated equations yields equations 12 and 16, which require the values of x, t, at t2n plus 1 and t2n plus 2. By solving these equations, we can obtain the unknowns x2n plus 1 and x2n plus 2 in terms of x2n. The values of x, t, at t2n plus 1 and t2n plus 2 are calculated using equations 19a and 19b, where alpha n and beta n are defined by equations 20. These coefficients are functions of the model parameters, the time step increment t, and the Wiener process w2n. The process is continued until the final time t is reached. The key idea is to use quadratic interpolation to approximate x, t, in each subinterval, and then use the resulting equations to progress the integration. The proposed method provides a way to integrate the system numerically, using a combination of interpolation and numerical integration. The accuracy of the method depends on the choice of the interpolation functions and the time step increment t. The authors present a stability, consistency, and convergence analysis of their proposed method for approximating the solution of stochastic diffusion equations. Firstly, they define mean square stability, which requires the sequence of approximations to converge to zero in the mean square sense. The authors then prove Theorem 1, which states that the proposed method is stable in mean square under certain conditions on the parameters. This is achieved by analyzing the mean square stability of the method, where they derive an inequality, 23, that must be satisfied for stability to hold. The same result is obtained for the other half-step of the method, leading to a general condition for mean square stability, 25. The authors conclude that the method is stable under the condition 26, which involves a combination of the method's parameters and the time step. Next, the authors define the local error and mean square consistency. The local error measures the difference between the approximation and the exact solution on a subinterval of the integration, while mean square consistency requires the local error to converge to zero at a certain rate as the time step decreases. The authors then prove Theorem 2, which states that the proposed method is consistent in mean square for approximating the solution of stochastic diffusion equations. The proof involves expanding the exact solution using the Ito formula and comparing it with the locally approximate value obtained from the method. By doing so, the authors show that the local error converges to zero at a rate proportional to the time step, thereby establishing mean square consistency. In summary, the authors have demonstrated the stability and consistency of their proposed method for approximating stochastic diffusion equations, providing a rigorous analysis of the method's performance and convergence properties. Here is a combined summary of pages 7 and 8 of the research paper. The authors establish the consistency of their proposed scheme for solving stochastic differential equations, SDEs, in mean square. Specifically, they derive upper bounds for the expected values of the squared errors, delta 2n plus 2, 2 and delta 2n plus 1, 2, using the interpolation error formula and the approximation x is x, t2n, approximately equals micro x, t2n, st2n, plus sigma x, t2n, w's w2n. As the time step increment t tends to 0, there exist constants k and k, such that e delta 2n plus 2, 2, is less than or equal to k increment t and e delta 2n plus 1, 2, is less than or equal to k increment t, respectively. This proves the consistency of the proposed scheme in mean square. The authors also discuss the conditional convergence of their method, citing the stochastic version of the Lax-Richtmeier theorem. They then present numerical results to demonstrate the performance of their scheme for solving SDEs. The errors are measured using the L1 error, L2 error, and L-infinity error between the approximate and exact solutions. The numerical experiments focus on the SDE dx, t, equals micro x, t, dt plus sigma x, t, dw, t, with initial condition x, 0, equals 1. The exact solution is given by x, t, equals x, 0, e, micro sigma squared, 2, t plus sigma w, t. The authors set sigma equals 0.5 and examine the stability region of their method, comparing it to the implicit M and Milstein methods. The results show that the proposed scheme has a superior performance, with the error decreasing consistently under mesh refinement. The authors also provide plots of the stability region, stochastic solutions, and error tables to illustrate the successful behavior of their approach. They observe that the computational results justify the theory of the stability conditions, with sample paths deviating wildly when the stability condition is not satisfied. The authors present a novel numerical method for solving stochastic differential equations, SDEs, which is compared to existing methods such as implicit Euler-Maruyama, implicit M, and Milstein. Figure 2 illustrates the stability region for the proposed method in Milstein, showcasing the improved stability of the proposed method for sigma equals 0.5. The approximate and analytical solution of equation 35, using the proposed method is presented in Figure 3, demonstrating its accuracy. Tables 13 compare the performance of the proposed method, implicit M, and Milstein in terms of L1, L2, and L-infinity errors for equation 35. The results show that the proposed method consistently outperforms implicit M and Milstein, with significantly reduced errors across all norms. Specifically, for n equals 2105, the proposed method achieves L1, L2, and L-infinity errors of 1.0671 times 10 to the 4, 1.2002 times 10 to the 4, and 1.8051 times 10 to the 4, respectively, which are substantially lower than those of implicit M and Milstein. The authors also investigate the robustness of the proposed method by simulating 10 trajectories for micro equals 1, as shown in Figure 4. This figure demonstrates the ability of the proposed method to accurately capture the behavior of the underlying SDE. The numerical results suggest that the proposed method is more accurate and efficient than existing methods, particularly for small time steps. The mathematical formulation underlying the proposed method is not explicitly presented in these pages. However, the authors likely employ a combination of numerical analysis and stochastic calculus techniques to derive the proposed method. The comparison to existing methods, such as implicit M and Milstein, provides a baseline for evaluating the performance of the proposed method. Assumptions regarding the underlying SDE and the choice of numerical parameters, e.g., time step size, are not explicitly stated, which may impact the applicability and interpretability of the results. Future work may involve investigating the robustness of the proposed method to different SDE models, noise types, and numerical parameters. This research paper presents a novel methodology for the numerical solution of stochastic differential equations, SDEs. The proposed method subdivides the time interval into subintervals and approximates the drift term over 3 successive node points using quadratic polynomials. The paper discusses the stability, consistency, and convergence properties of the proposed method, demonstrating its superior performance compared to the implicit Euler-Maruyama and Milstein schemes through numerical examples. The authors also discuss potential future work, such as extending the method to general forms of SDEs. The paper begins by outlining the importance of solving SDEs, which are fundamental in modeling various phenomena in physics, biology, and finance. It then provides a comprehensive review of existing numerical methods, including the Euler-Maruyama, Milstein, and Runge-Kutta schemes, along with their limitations and challenges. The proposed method is then introduced, which involves approximating the drift term using quadratic polynomials and applying the Ito formula to approximate the stochastic integral. The paper proceeds to analyze the stability, consistency, and convergence properties of the proposed method, demonstrating that it exhibits better performance than existing methods. This is supported by several numerical examples, including the simulation of a stochastic oscillator and a stochastic logistic population model. The results show that the proposed method provides more accurate solutions and is computationally efficient. The authors also provide a detailed list of references, highlighting the extensive literature on numerical solutions for SDEs. This includes works on various numerical schemes, stability and convergence analysis, and applications in different fields. The paper concludes by emphasizing the potential for future research in this area, particularly extending the proposed method to more general forms of SDEs. In summary, this paper introduces a novel numerical method for solving SDEs, which outperforms existing methods in terms of stability, consistency, and convergence. It provides a comprehensive review of existing literature and demonstrates the effectiveness of the proposed method through numerical examples. The paper's findings contribute significantly to the field of stochastic differential equations, paving the way for further research in this area. The paper explores the application of the linear Steklov method for solving stochastic differential equations, SDEs, with non-globally Lipschitz coefficients. This approach is a variation of the classical Steklov method, which has been widely used in solving partial differential equations. In the context of SDEs, the linear Steklov method is particularly useful as it can provide strong convergence and simulation capabilities. The authors cite several seminal works on SDEs, including those by Gard, 26, Mao, 27, and Maruyama, 28. These references provide a comprehensive understanding of the mathematical framework and applications of SDEs. The paper also draws upon the work of Kumar and Agrawal, 29, who developed an approximate method for numerical solution of fractional differential equations, which shares some similarities with the approach presented here. In addition to the theoretical background, the authors discuss practical aspects of implementing the linear Steklov method. They reference Roth's report, 30, on approximations of solutions to a first-order stochastic partial differential equation, highlighting the importance of considering the specific properties of the coefficients involved in the SDEs. The paper's main contribution lies in its extension of the linear Steklov method to handle SDEs with non-globally Lipschitz coefficients. This is achieved through a series of mathematical transformations and approximations that allow for the derivation of a discrete time approximation scheme. The proposed method is shown to be convergent under certain conditions, making it a viable alternative to existing numerical methods for solving SDEs. Overall, the paper presents a novel approach to solving SDEs with non-globally Lipschitz coefficients using the linear Steklov method. By leveraging the mathematical foundations established by previous researchers and applying them to practical problems, the authors have developed a new tool for researchers working in this field. The paper concludes by outlining potential future directions, including further analysis of the proposed method's convergence properties and its application to more complex stochastic systems.